Okay, so the next thing is we want to define what is a finite set and an infinite set. Now, before we go to the definition, we take an example. I take the set A to be the numbers say 0, 2, 4, 8, 16 and 32. Now if I count the number of elements, we call this the cardinality of the set, and we know that it's going to be 6, which is a finite number. So in this case we say that A is a finite set. Now if I take the interval, the open interval 1, 2, what is the cardinality of this interval? Now if I try to count these numbers, we know that this is an interval in the real line. So I have infinitely many numbers between 1 and 2. So in this case, the cardinality of B is undefined, or we call it infinite. So we have an infinite set, that means the cardinality is infinite, and in a finite set the cardinality is finite. Now if you want to do a proper definition of a finite set, that means if I can define a function from a set A to the set of numbers, say 1 to up to n, and if f is 1 to 1, then we say that the set A is finite. Otherwise we say the set is infinite. Now if I take the set of integers, now these are the numbers, the whole numbers. So we have -5, -4, and it'll continue from, it'll go back to -6, -7. So these are whole numbers. Now what is the cardinality of this set? And again we know that the cardinality of this set is infinite. Okay, so and if we take the set of rational numbers, again we know that we have infinitely many rational numbers, so the cardinality is infinite. Now if two sets, so I have two sets A and B, since we are talking about the real line, we'll take these sets to be subsets of the real line. We say that A and B are equipotent. It's not a term that is common. We say that A and B are equipotent, or they have the same cardinality if I can define a one-to-one function from A to B, or a one-to-one correspondence. Or basically, if it's a finite set, that means the cardinality of A is equal to cardinality of B. So that's about finite and infinite sets. And then we have the other word, which is important, is going to be countable. Now what's the difference between countable and uncountable? So we'll take the same example. If I take the set of real numbers, the set of integers, the set is infinite, but I can count these numbers. I can count as 1, 2, 3, -1, -2, and 3. So in this case, this is a countable set, but it's an infinite set. So a set is called countably infinite so set A is countably infinite if A is equivalent to the set of positive integers so that you can count. That means you should be able to define a one-to-one correspondence between A and the set of positive integers. So a finite set is always countable. So the finite implies countable, but not the other way around. And a set which is not countable is called uncountable. So can you think about an example of an uncountable set? So the most obvious example is the set of real numbers. So we cannot count the real numbers. So this is an example of an uncountable set. Or if I take any open interval, that's going to be uncountable. So if you take, so this is some properties. If I take a subset, so you have a finite set, and if I take a subset, then this is also obviously going to be finite. And similarly, if I take a countable set, and if I take a subset, the subset is going to be countable. Now so these are the first two properties. Now if a set contains, so you have a set A, now this set contains a set B, and if B is infinite, then this implies that A is also infinite. And similarly, this happens to uncountable sets as well. Say if B is uncountable, then the superset A is also uncountable. And then we have this theorem that says if you have a finite sequence of sets, if each of these sets is finite, then the union of this set, so I can write the union as union of I from 1 to n is finite, and the Cartesian product, so we can denote the Cartesian product by product I from 1 to n is finite. And if each AI is countable, then Cartesian product I from 1 to n is countable, and the union of ai is countable.